There's another way to find the equilibrium constant for this generalized reaction. We know that pressure is proportional to concentration for gases in a closed system. Therefore, the equilibrium expression can also be written in terms of pressure. And everything is the same here as the previous expression, except instead of this term, right, which was the concentration of species C, we take its partial pressure, and again we raise it to the same coefficient as we did there. So P sub A, partial pressure of reactant A, B would be partial pressure of reactant B, and then C and D would be the products.
Let's discuss more specifically what happens at equilibrium for a reaction when everything is a gas. So equilibrium constants for reactions occurring exclusively in the gas phase can be expressed as either Kp or Kc values. Kp expresses the equilibrium amounts in pressures, and Kc expresses the equilibrium amounts in concentrations. So given the following reaction, I can write both Kp and Kc equilibrium expressions because, as you can see, every product and every reactant is a gas. So Kp would be the pressure of each product over the pressure of each reactant. And of course, don't forget that if you have a coefficient, you have to raise to that power. And we use parentheses here because we're talking about pressure and not concentration. And then we can also write Kc as a ratio of the concentrations of the products, to the concentrations of the reactant. So it looks very similar, but in one we're talking about pressures, and in the other we're talking about concentrations or molarity. So what is the relationship between Kc and Kp for a gaseous equilibrium? So if I plug this into the expression for Kp for each substance, the relationship between Kc and Kp looks as follows, where Kp is equal to Kc times RT, R being the ideal gas constant, T being the temperature, to the power of the change in the number of moles, where delta mole is the moles of gaseous product minus the moles of gaseous reactant. Okay, so for example, calculate Kc for the following reaction at 10 degrees C. So we have 3H2 plus N2 produces 2NH3. Again, everything is a gas, and we're given the value of Kp. So Kc is equal to Kp, which we see here as 0.045, divided by RT, which I've already calculated, RT 23.2, to the power of moles of product minus moles of reactant. So we have 2 moles of product and 3 plus a little invisible 1 there, 4 moles of reactant. So 2 minus 4 is how we get this exponent of minus 2. And therefore we get a Kc equal to 24.2. Now, if the change in the number of moles is 0, then I'd have this RT to the power of 0, which is 1. And Kc will then equal Kp. So when there are equal number of moles of products as there are reactants, Kc will equal Kp.